Today, we're going to talk about a hidden force that honestly powers almost everything around us. It's called electrochemistry, and it's how we turn a literal pile of scrap metal into the super pure materials inside the phone in your hand. It's an incredible transformation.
I know, it sounds like a total contradiction, right? How could a pile of junk, of discarded, impure copper scrap, hold the potential for some of the purest metal on the entire planet? Well, the secret to unlocking it is a process that's both, really elegant and just unbelievably powerful.
So, how do we make that leap from scrap to supermaterial? Well, it all kicks off with something we call the purity problem. And it's a challenge that comes directly from our world's frankly insatiable appetite for high-performance stuff. I mean, just think about it for a second. Every single wire, every circuit board, every electric car, and every giant wind turbine, they all depend on copper's amazing ability to conduct electricity. But here's the catch. For that electricity to flow as efficiently as possible, the copper has to be almost perfectly pure. We're talking 99.99% pure. Even the teeniest little impurity can mess with conductivity, create unwanted heat, and just waste precious energy. So how in the world do you get a pile of scrap metal that clean? The answer, it turns out, is to give that impure copper a very, very special kind of electric bath. And this is where we get to meet the star of our show today, electrolysis. Okay, so this is a basic electrolytic cell. Now, it might look like something straight out of a high school science fair, but this simple setup is the engine behind a massive industrial process. You've got two electrodes, an anode and a cathode, and they're submerged in a conductive liquid we call an electrolyte. Hook them up to a power source, and the real magic begins the moment you flip that switch. All right, let's follow the journey of a single piece of copper. It really happens in four main steps. First, you take your impure scrap copper and you make it the positive electrode, the anode. Step 2, you dip that anode into a bath of copper sulfate. That's our electrolyte. 3, you apply a direct electric current. And 4, this is the cool part, you just watch as ultra-pure copper atoms literally move through the solution and plate themselves onto the negative electrode, the cathode. So let's zoom in on the starting line. The anode. This is the positive terminal. What happens here is the electric current basically forces the impure copper atoms to let go of some electrons and dissolve into that electrolyte bath as positively charged copper ions. You can pretty much think of this as the dissolving station. So, where do all those copper ions go? Well, they're positively charged, so they get pulled across the bath to the cathode, which is the negative electrode. It's like a magnet. When they get there, they grab some electrons and turn back into pure, solid copper atoms. And they just slowly, atom by atom, build up a beautiful sheet of pristine metal. This is our collection station. Okay, but what about all the other junk that was mixed in with the scrap copper? The zinc, the iron, the gold? This is where the process gets really, really clever. It acts like an incredibly precise chemical sorter. This slide really shows that sorting process in action. So over on one side, at the anode, the electric current is just right to dissolve not only the copper, but also any metals that are more reactive, things like zinc or iron. But then on the other side, at the cathode, only the copper ions have that perfect electrical sweet spot to turn back into solid metal. So what about those other impurities? They're just left floating around in the bath, totally ignored. And what about the metals that are less reactive than copper? Well, the current just isn't strong enough to dissolve them in the first place. So as the copper anode around them disintegrates, they just fall off. They drift down and collect at the bottom of the tank as this kind of sludge. And here is where the whole thing becomes just economic genius. That slime isn't just waste. It's often loaded with precious metals, gold, silver, platinum, all the stuff that was hiding in the scrap. In fact, recovering these valuable metals is so profitable, it often pays for the entire energy bill for the recycling process. It's not a byproduct, it's a core reason the whole system actually works. So up to this point, we've seen how electricity can force a chemical reaction to happen that wouldn't happen on its own. But, that's only one side of the coin. Now let's flip it over and look at the other face of electrochemistry. Not forcing energy in, but getting it out. Electrochemistry really has these two different modes. The copper refining we just looked at uses an electrolytic cell. You put energy in to force a reaction to happen. The other kind is a galvanic cell, which we all know by a much simpler name, a battery, and it does the exact opposite. It takes a chemical reaction that wants to happen all on its own and harnesses it to get energy out. And this, of course, brings us to a device that's probably within arm's reach of you right now. Let's take a look at the battery in your hand.
because it's basically just electrochemistry to go.
So, inside your phone's lithium-ion battery, you've got the same basic cast of characters: an anode, a cathode, and an electrolyte. When you're using your phone, we call that the discharge cycle. Lithium ions naturally want to flow from the anode to the cathode. That movement is what creates the electric current that lights up your screen and powers everything else.
And charging? Well, charging is literally just electrolysis in reverse. It's the same principle. When you plug your phone in, the power from the wall outlet forces those lithium ions to flow backward, against their natural direction from the cathode back to the anode. It's that forced, non-spontaneous reaction that crams energy back into the system, getting it ready to be used all over again. You know, there's a good reason lithium-ion batteries are king right now. They pack a massive punch in a really light package. They don't have that annoying memory effect that old rechargeable batteries had. And they hold their charge really well even when you're not using them. The big trade-off? That electrolyte, the stuff that lets the ions flow so easily, is flammable. And that's exactly why safety in battery design is such a huge deal. So we've gone from purifying metals to powering our entire digital lives. Let's wrap this all up by looking at why electrochemistry is just so absolutely critical for our future. Let's start with a really big number. Recycling 1 ton of copper using electrolysis, it uses up to 85% less energy than making that same ton of copper from brand new ore dug out of the ground. That is a massive saving, both for the environment and for the economy. And really, this is the key takeaway. This technology isn't just about making clean metal. It is a fundamental pillar of a sustainable, circular economy. It gives us the power to take our constantly growing piles of waste and turn them back into the high-value, super pure resources that we desperately need. So this one branch of science takes gunk from a scrap heap, refines it to near perfection, and then uses those exact same principles to power the incredible devices we build with it. It's a perfect, elegant circle. The only question left is, what's the next big challenge we're going to ask it to solve?